My name is Andrzej Pietrasiewicz, and today I will tell you how to create your own USB gadget without writing any kernel code. We will take it even one step further, and I will show you a gadget implemented entirely as a shell script. But first things first, I will tell you what a USB gadget is, and I will tell you what is its relation to the Linux kernel, and I will also tell you about one problem related to the traditional way of composing such gadgets, and I will show you how the config.sh interface helps, and we will see two live demos. And the second demo will be a USB gadget implemented entirely as a shell script. Then I will go through the available user space tools, and we will be finishing with the questions and answers session. Okay, so in USB there are two distinct roles, the host and the device. And it is a host-centric bus, and its purpose is to extend the host with some additional functionality, be it a mouse, a keyboard, a broadband modem, or whatever you can think of. There are many standard functions available, like serial communication, various flavors of Ethernet, mass storage, human interface, webcam audio, and so on. A USB device can provide more than one such a function at the same time. But life is even more complicated. Why? Because the USB standard says that the functions must be grouped into configurations, and there must be at least one configuration in a device. Even if there is just one configuration, it looks like there is quite a lot of data to be passed from the host to the device. But what are configurations after all? Well, they were meant by the USB standard creators as host selectable views on a device, offering different power consumption from host's power supply or different bandwidth usage of the bus. So even if there's just one configuration, there's quite a lot of data about the device to be passed from the device to the host. This kind of information is encoded in data structures called descriptors. There are also USB strings which are, well, just that. Strings which can be presented by the host to the user and which are meant to be some human understandable description of the device. Now the question is when and how this kind of information is passed from the device to the host. It happens during a process called enumeration. And based on the information received, the host decides what to do and how to talk to the device. It's exactly the same process as when you connect your mobile phone to a PC to download pictures from root Linux conference or to use it as a broadband modem. In USB communication, some parts must be implemented in hardware, while some other can be implemented in software. So let's have a look. Today, our focus is on a device part. We treat the host as a black box. The device is connected to the host with a USB cable, which plugs into a component called PHY, which is capable of transferring zeros and ones over the physical medium. On top of PHY, there is the UDC block, USB device controller, which handles the general logic of USB communication, but which does not know anything about actual functionality provided by the device. It provides so-called communication endpoints, which are unidirectional data streams from the host to the device or from the device to the host. The actual functionality is implemented in this block marked with question marks. There is, however, one endpoint called endpoint 0, which is bidirectional. All USB devices must provide it, and it is endpoint 0 which is used for transferring strings and descriptors when the device is enumerated. Today, our focus is on USB devices which are machines running Linux, equipped with PHY and UDC, and whose actual functionality is implemented in software. Exactly like with your mobile phone, where the way it is seen by the PC is fully software defined. You choose whether you want MTP, PTP, mass storage, or perhaps a broadband modem. So now let's learn something about this software implementation. First of all, the USB standard has no name for this kind of software running on top of UDC. So kernel developers came up with the name USB Gadget. This name refers only to Linux implemented functionality of a USB device. Now, until around 2013, 2014, there were only predefined gadgets. Each gadget provided only one functionality, and each gadget was implemented as a separate kernel module. So you might start seeing a problem here. Even though there exists so-called composite framework, which factors out all the common stuff and delegates function-specific stuff to function files, the composition of traditional gadgets was hard-coded. So, for example, if you wanted a gadget with some set of functions, you create a kernel module. If you want only a slightly different set of functions, you create another kernel module, and so on. There are two problems with this approach. First, you need to know how to write kernel code. Even if you overcome this difficulty, then you need to maintain your code, or have the community maintain it, but that's not an easy task either. And indeed, the kernel developers have decided that a proliferation of kernel modules happening just because some static data is different is not the way to go. Then what to do? The idea is to separate code from data, to decouple the information on actual gadget composition from implementation, and only provide building blocks out of which the user composes their gadget at runtime. There were several attempts at implementing this kind of functionality. Android needed it long before it was available in kernel, so they invented their own way. Then there was the CCG, Configurable Composite Gadget, which was an attempt at generalizing the Android approach and making it independent of Android. But eventually, kernel developers have chosen the configFS approach. What is configFS? It is a virtual file system which is very similar to sysfs, both in the way it is used and in the way it is implemented. The difference is the intended purpose. While sysfs is a view into the system, the configFS is a way of creating and destroying kernel components whose lifetime is decided by the user. Let's see how this idea can be applied for composing a gadget compared to the traditional approach. So in the traditional approach, everything was hard-coded, defined at compile time. While in the configFS approach, initially there is nothing. Then the user creates some configurations and functions, associates functions and configurations, the user can change their mind, add some more. When finally the user is satisfied, they must somehow commit their gadget. This way, dedicated kernel modules containing different compositions of gadgets are not needed anymore. It turns out that this kind of activities map very nicely to file system operations. To create something, you make a directory. To remove it, you remove the directory. To specify a value, you write to a file. To get a value, you read from a file. To group things together, you use a symbolic link, and to ungroup things, you remove the link. So here is the command reference, very simple shell commands. So why don't we give it a try? I will go relatively quickly through this slide, and then I will repeat the same commands on my target board. So first we go to the canonical config.fs mount point, and whenever the composite framework code is in the kernel, the USB Gadget directory is available in config.fs. When we create our first gadget, we give it a short and easy name G1. Inside its directory there are a bunch of directories and files. So let's give our gadget some identity. We specify vendor ID and product ID, and we specify some strings for our gadget. 409 hex here is for US English. In practice, probably no one uses anything else. Now let me repeat the same commands on my target board. It's an Odroid U3. Here it's a machine running Linux. And it's of course equipped with a UDC. Now I need to bring my demo screen to the display. Okay. All right. Looks like I have some. I cross-checked it this morning and it worked. Bad fate. There are only 2 slots.
Would you like spare Odroid or serial or something?
No idea what's happening. The demo effect. Okay. Sorry about that delay. So you can see the device booting. Once it boots, I will repeat the commands I've gone through in the slides. Okay, so the device. Where is that pointer? Okay, the device has booted. Now let me go to the canonical config.fs mount point. Sys kernel config. There's nothing in here, so let's bring the composite framework.
C missing. Leave composite. C letter.
Lib.
Composite.
Okay. I'm sorry. That's better. Thank you. You're the best audience. The most helping one. Okay, so we have a USB gadget directory. There, let's create our gadget. mkdir USB gadget G1. Let's enter its directory, USB gadget G1. Okay. we have some files and directories there. Now let's give our device some identity. I'm borrowing identity from an R&D's gadget. It will be an R&D's gadget that is a flavor of Ethernet, containing one configuration and one function. Echo A for A1 to ID product. Okay. Now let's create some strings. Strings 409. Okay, let's see what's in there. Strings 0x409. We have 3 strings available, so let's say root Linux conference to strings 409 manufacturer. Now let's say RMDs to strings 0x409 products. Echo version 1 to strings 409 serial number. Okay, cat strings 0x409 everything. Okay. Now let's create. Let's go back to the slides. So we have an empty gadget now, which has some identity, but we need a function. So we use RMD's function in this case. We create one configuration. We create configuration string, again 409, and we assign our function to a configuration. At this point, the structure of our gadget is complete. It's in memory, but the gadget is not active yet. In order to activate it, we need to specify the UDC name to the UDC attribute. The question is, where to get UDC name from? Well, it's available in sysfs. In this board, there's just one. So let's use that. Okay. So we create a function, RMDs USB 0. Okay, we create a configuration, and inside it we create its string, C1 strings OX409. We echo conf1 to config C1 strings X401 configuration. Okay, and we now this is the contents of the configuration directory. Now we assign our function to our configuration. So we functions are in this USB 0 to configurations C1. And now you see that the function is assigned to the configuration. And it's time to bind our gadget. Echo 12480000. Thank you, device 3, HS OTG, to the UDC attribute. Okay, something has happened. We have a new USB 0 interface at the device side. Now let's connect our device to the host. And let's see what happens. The top right terminal is the device terminal, the host diagnostic messages. So let's see what happens. Which command did you use to list the devices? You can find the available UDCs in sys plus UDC over here. So you want to see the command which I used.
Scroll a little bit up.
Yeah. That was the one. That one.
No, the left.
So it's found in network devices.
This one.
No, it means all of the devices.
All of the devices. Yes. Yes, precisely. Do you know what USB means? It means usually slightly broken. Okay, it seems I'm done. Okay, so but I have another problem. Definitely today I'm suffering from too many demo effects. Now I know why I started earlier. I think I need to reboot the device. It's crazy. What do I do? The other thing is to reboot the host. Okay, so now I'm trying to restart a very nice demo. Okay, so the top left terminal is my device. This kernel config control leave composite. Okay, and here USB gadget G1, CD USB gadget G1, echo 0OX. 5 to ID. Number equal 0x A4A1 to ID product and MKDir strings OX49 equal context strings. Thank you. You're the most helping audience. Strings manufacturer equal strings product equal version 1.0 to string, strings 49 serial number and idea config C1 and idea strings OX49 equal conf1 to config C1 strings. Okay, and here functions and this USB 0. ln minus s functions and this USB 0 to config C1 equal 1248000 HSOTG to this attribute. Okay. So we have diagnostic messages. Okay. And now let me configure the interface at the device side. I have config USB 0. Okay, let's do the similar command at the host side, but first I must gain appropriate power. Okay, I have good power now. So I have config USB 0, 1, yes. Thank you. And now not 1, 3. Okay. So my host is pinging the port. Let's try the ping the other way around. Ping. Okay. So the port is not connected with Ethernet cable to the host, and yet we are able to ping each other. Alright, so let me stop it and let me unbind the gadget from the UDC. We do it by specifying an empty value to the UDC attribute. Okay, you can see that the host has noticed that the device has disconnected. And to remove the gadget structure completely from memory, you need to remove all the symbolic links, all the directories you created so far. But I won't be doing it right now. So let's get back to our presentation. I want to tell you about one detail of implementation, just one detail. So, the Composite framework maintains a list of available USB functions. And whenever the user creates a function directory, the list is consulted. And if the function is in the list, the appropriate module, the directory creation proceeds. If the function is not in the list, then a module is requested based on function name. If it loads, the function is appended to the list, and the function directory creation proceeds. If the module doesn't load, because it's not found, then nothing is appended to the list, and the function directory creation fails. Now, the question is what to do if you want your very own function. There are two options. You can write a kernel module implementing it. It's the first option. So you implement your function as a kernel module, you follow the config.fs style, and you can use your function as a component of a gadget composed with config.fs. It's a valid approach. However, we exchange writing an old-style gadget kernel module for writing a perhaps smaller kernel module implementing our function. So why not use it in user space? Enter function.fs. What is function.fs? It is a very special USB function, and as a USB function, it can be used as a component of a gadget composed with config.fs. This function is very special because it actually delegates the implementation to user space through a dedicated virtual file system. The idea is to implement data transfers between the host and the device by reading and writing some virtual files inside this virtual file system. There can be more than one instance of function.fs in the system, so you can implement more than one function at the same time. Under the mount point of each function.fs instance, there is an EP0 file, which will be used for receiving control events from the host, but before the function is active, it will be used to write US descriptors and strings to the kernel. The kernel then verifies those descriptors, and if it can handle such a request, it creates appropriate number of EP files according to what was in the descriptors. Then we read and write appropriate files, and this way we transfer data from the host or to the host. Function.fs is another virtual file system today, so let's see what's its relation to config.fs. With config.fs, you can only create function.fs instances, but function.fs instance directory in config.fs is intentionally empty, because the actual functionality is supposed to be implemented elsewhere with EP files. Now, armed with this knowledge, let's create our shell script, Gadget. So the design is like this. We will implement a loopback function, which will retransmit to the host whatever it receives, converting the small letters to capital letters. The gadget will be composed with config.fs, and it will be composed of one function and one configuration. Actual function will be implemented as a shell script with function.fs, and we will ignore EP0 events, which is a bad design, but we are fine with that for this demo. We will test our gadget using USB serial generic driver. That is, the USB serial generic driver will create the FTTY USB something device for us, and we will expect to read back from that device whatever we write to it, except that it will be all capital letters. So now let me go through the first part of the script composing our gadget. So we go to the config.fs canonical mount point. With mkdir with the -p switch, we create in one go a gadget directory, and inside it a function.fs instance called upcase. This part of the name is important because later on it will be used as a device name when mounting this function.fs instance. Then we create, we enter our gadget directory and create in one go a configuration, and inside it a strings directory, but we don't care specifying actual value of the string. We will leave it empty for the purpose of this demo. We assign our function to our configuration, and we give our gadget some example identity. Now let me repeat the same commands on my target board. Actually, I have a shell script which contains exactly the same commands. Let me just run it. Okay, something has happened, and now we are back to our slides. And we need to implement finally our function. As I said, the config.fs directory of function.fs is intentionally empty. We need to mount function.fs somewhere, so why not just use the directory? Now, does anyone know what this bash syntax means? Can't hear anyone.
Read from the string input 3 and out to the specific. No.
So it can be considered a kind of redirection. It's the way we use file descriptors in bash. The question is, why to use file descriptors at all? Well, the answer is because of the way function.fs is implemented. Whenever you close EP0, it means you are done with your function. It ceases to exist, and your gadget gets unbound from the UDC. This way, we open it, and we keep it open for the lifetime of our gadget. Now we write USB descriptors to the EP0 file. So we redirect the output of some command to our EP0 file. The xxd command is a command which, given the -r, -p switches, takes a hex dump and creates a binary representation of it. So we write descriptors in binary form. The number 3 here says, as the name implies, we will be using function.fs version 2 header. Now, how much decimal is 27 hex?
What, 39?
39. And indeed, there are 39 bytes in this block. Now, the number 2 here says there will be only high-speed descriptors. And then the high-speed descriptors follow preceded by the number of high-speed descriptors. There will be 3. A1, A2, and A3. The first byte of each descriptor is its length. 9 bytes, 7 bytes, 7 bytes. The second byte is descriptor type. Number 4 is for interface, which is our function. and number 5 is for endpoints. I won't be going into details. I want just to mention that the number 2 here says there will be 2 descriptors, 2 endpoint descriptors, and indeed there are. Number FF here says it will be vendor specific class. Our function is very specific. And number 81 and number 02 here specify the descriptor address and direction. In a very similar way, we specify strings. So number 2 for strings, 20 is 32 decimal. There are 32 bytes in this block. Number 1 here and number 1 here say that there will be 1 string in 1 language version, 409 little endian for US English, and then actual content follows, terminating with an byte. It says upcase filter. So this was the fun part, and now the boring stuff. So it's a very quick and dirty implementation, so we simply give kernel some time to create our endpoint files. Now you know this syntax. So we open EP files and keep them open for the lifetime of our gadget. And indefinitely keep copying chunks of up to 8 kilobytes from host output to host input descriptor, converting to uppercase on the go. So that's our shell script implementation of our USB gadget. We must not forget to bind actually the gadget, and now keep your fingers crossed, because we will try to repeat the same commands on the real device. Again, I have another script which implements the commands we just saw. So let me put it into background. Okay, and now let's bind our gadget to the UDC. GT2 sys kernel config USB gadget single function UDC. Okay, so we see 2 things here. Our gadget has been bound and it has been noticed by the host. We can see ABCD and 1, 2, 3, 4. So now we tell the generic serial driver at the host side about this new device that I must gain root power. Okay, so echo ABCD 1, 2, 3, 4 to sys bus USB serial generic no, not yet. Drivers generic new ID. Watch the host diagnostic messages. A new TTY USB 1 device has been created. So let me configure this device. I will issue this kind of command. It's not interesting for us. Okay, so now let us see what's inside the device. Nothing, and should be nothing, because we haven't written anything to it yet. So let's echo root linux conf to dev TTY USB 1, and you can see all capital letters here. Now let's write some more. Perhaps etc password to dev TTY USB 1. Okay, all capital letters, password file. Let's write some more. Okay, diagnostic messages, all capital letters. So that's our gadget implemented as a shell script. Now let me terminate it. Okay, and coming back to the slides. Now I want to tell you about user space. As you saw with config.fs, the ease of use is not a priority. Composing a gadget is not difficult, but it's somewhat tedious. You need around 20 commands to create a simple gadget. Well, 16 to create a simple Ethernet gadget. So what to do? It's not too difficult, but yet much more difficult than the traditional mod-probe Ether. Well, you can either write a shell script or maybe use some dedicated user space program. And fortunately, there exists a libUSBGX library, which is a wrapper for config.fs operation. The maintainer of this library is in this room. It's not me. It handles all the stuff related to composing a gadget with config.fs, but I want to mention just one very important feature of that library. It's capable of exporting and importing gadget composition to and from a file. From a file like this. So it's a plain declarative configuration file as opposed to imperative style shell script. So using this, you don't need to know where to look for config.fs, what kind of things to look inside config.fs, what kind of things to create, what kind of values to write. You simply specify what you want created rather than how. There exists a GT tool, a Gadget tool, which is a command line tool which uses libUSBGX. Let me show you this command in action on the device. So, with this tool, we can see that we have two gadgets. Let us get rid of them. GT RM-RF G1, GT RM-RF single function. We cannot remove it yet because we have function fs mounted. So let's unmount sys kernel config single USB gadget single function functions. Okay, and now let us repeat it. And no gadgets available. Let's cross-check. Let's sys kernel config USB gadget, nothing. And I have a configuration file of Ethernet gadget. Yeah, so it's basically saying that there is one configuration, vendor ID, product ID, and there's just one function, ECM, so another flavor of Ethernet. So let me run an equivalent of old-style mod-probe Ether with this gadget tool. So GT load file, and we need to give our gadgets a name. Okay, so you can see that the device has been enumerated and that the host has noticed a new device, and registered a new network interface. You can see the product manufacturer and serial number are essentially the same things that are in the configuration file. Okay, so okay, one more thing. Some features in the Gadget tool are not yet implemented, yet it is very useful as an equivalent of old-style mod-probe Ether. contributions are welcome.